And welcome back. We are now going to talk about copy constructors, which are very important when we start looking at things like such as how to clone. But with today's, we're not going to be able to dive fully into it. So, because there's going to be a difference as we look at this, that we look between the difference between making a shallow copy and what's known as a deep copy. So cloning and copying kind of go hand in hand when we start looking at this in programming. The way Java handles cloning and object copying in general is kind of complicated sometimes, and at the same time can be really subtle but difficult. Some people think, cloning was done simply very poorly in Java, and it's oftentimes ignored completely and instead is defined with its own methods for copying objects. And while you could just dismiss Java's approach, it is a good idea to see what that approach details, because it could, of course, help you if you want to actually implement that or you come across code that has implemented it. So linked data structures such as linked lists are an excellent setting for discussing cloning because they're very useful for discussing that deep versus shallow copying. Now we're going to today present a relatively simple way to define copy constructors and the clone method, but this approach unfortunately is only going to allow us to produce shallow copies. Now later on, of course, we will look at a deep copy method and do so within the prescribed rules that Java has within its documentation. So simple copy constructors and clone methods are what we're going to use to start. And we're going to actually use this class called new linked list. It's a generic class. It's going to have a copy constructor and a clone method definitions that we could have went and added to our previous class, linked list 3. Now, the real work, of course, is being done by the private helping method copy of. So our focus today will be on that method. Now, that method takes an argument that is a reference to the head node of a linked list and returns a reference to the head node of the copy of the linked list. The easiest way to do this, of course, is just to return the argument. This, however, simply produces another name for the argument list, and we do not want another name. We want instead another list because we're trying to make a copy. So the method is going to go down the argument list one node at a time with the position, of course, and therefore make a copy of each node. Now, when we start looking at how do we actually add nodes into this new list, well, the linked list of the calling object is built up node by adding these new nodes to its linked list. However, we do run it eventually into a complication. We can't simply add the new nodes to the head or the start end of the list being built. If we did, then the nodes would just end up in the reverse of the desired order that we want them to be. So the new nodes are therefore added to the end of the linked list being built. Now the variable type node t is kept positioned at the last node, so it's always possible to add nodes at the end of the linked list being built, because otherwise, if we add them to the start every time, like I said, it's going to be backwards. This way, the copy of the list and the calling object creates so the order of the nodes is preserved, because we don't want one to go, for example, 1, 2, 3, 4, 5, and the other one to be like 5, 4, 3, 2, 1, because it's going to, again, be two different orders then. Now, if we talk about that copy of constructor, this is defined by using the private helping method, of course, copy of, to create that copy of the list of nodes. Other details of the copy constructor and the clone method are done pretty much in a standard way. Although the copy constructor and clone method each produce a new linked list with all new nodes, the new list is not truly independent because the data objects are not cloned. And that's, of course, going to lead us into having to deal with some exceptions here. Now, a generic data structure, such as the class linked list 3 that we previously looked at, is likely to have methods that can throw exceptions. Situations such as like a null argument to the copy constructor might be handled differently in different situations, so it's best to throw a null pointer exception if this happens and let the program who is using the linked list handle that. And this is what we did previously when we looked at linked list 3. Now, a null pointer exception is an unchecked exception, which means that it does not need to be caught or declared in the throw clause. Remember, unchecked means it's not going to be involved with the compiling of it. Now, when thrown by a message of a linked list class, that exception is simply treated as a runtime error message. That exception can then instead be caught in a catch block if there is some suitable action that can be taken for that exception. Now we do start running into some pitfalls. As we mentioned before, this is a shallow copy, not a deep copy. And one of that is because the clone method itself is protected within the object class. So when we start defining our copy constructors and our clone methods for our generic linked list, we would like to say, hey, let's clone the data of the link being copied. Well, we would like to change the code in the help method copy of, such as the following: new head equals new node, and we get the position data.clone, null, end is now the new head, position equals position.link, while position is not null, so let's copy the node to the position and list. End.link equals new node t, position.data.clone null, end equals end.link, position equals position.link. That would have been perfect. However, coming back to copy of, you can notice that what we wanted to do is identical to that code, except for the addition of the invocations of clone and the typecast that we have to do. Now, of course, those typecasts are necessary because Java thinks that clone is going to return a value of type object. If this modified code with the clone method would compile and the type plugged in for t has a well-defined clone method that makes a deep copy, well, then this modified code would produce a truly independent linked list with no references in common to the list being copied. However, what we're going to run into is that this code will not compile. All right, if we try to compile it, we're like, hey, we got it in here, we're going to go with this, we're going to get an error message. And the error message is going to say that the method clone is not protected in the class object. Sure, we might have used a type t, not the type object, but remember, any class can be plugged in for t because that's the whole point of it being generic. Now, when the generic linked list is compiled, all Java knows about the type t is that it's a descendant class of object. And because the designers of that object class chose to make the method clone protected, you simply cannot use the clone method in the definition for methods such as copy of. So because we have a protected clone method we got to work with, we have to wonder, well, why did we have to have this limitation? Why was it labeled protected? Well, the primary reason was for security purposes. If a class could use the clone method unchanged from object, then that would open the possibility of copying sections of, for example, memory unchanged and unchecked, and it might actually give unauthorized access to system memory. This problem, of course, is made more serious by the fact that Java used to run programs on other machines across the internet. So, yeah, obviously you can see they're starting to have some huge flaws that could potentially be exploited here. So this is getting us back to the root issue of having a shallow clone copy. In many situations, the copy of version that we had in linked list 3 without the use of clone was good enough. But there is a way to get a true deep copy. One way to get a deep copy is somehow restrict the type t to classes and to have a public clone method that can actually make the deep copy. And we can do this, and we're actually going to start discussing the approach for this in our next lesson. And if we go ahead and look at our new linked list class here, just so we can take a look at that code, one of the things you'll see here, just to kind of reiterate how that works, if we look here at this constructor, this is how we produce that new linked list. But notice we note it is not a true deep copy, and we're going to also throw a null pointer exception if other is null. So other, of course, being the other list here. And so if you look here, we are saying, hey, if this list is null, throw a null pointer exception. Otherwise, the head isn't equal to null. Set the head to null. Otherwise, make a copy of it. And of course, the copy of is this method down here, which of course is creating that copy of. It does not return a true deep copy. Here's our clone method, all right, that we are going to kind of really start picking apart here. And both of these methods here, again, remember, this is not going to get us to where we want things to be. This is a good start. And so this is a great way for us to make a copy of these different things, because remember, this method right here, this copy of node, is not going to actually be accessible to the programmer. Instead, it's going to, you call like a constructor, or you can call the clone method here to go ahead and try to create that copy of that list. But again, we haven't really explored how do we make that true deep copy, because remember, right now, the data between these two lists, if you make a new linked list list 1 and new linked list 2, they will effectively share data, all right, because we haven't truly made them deep copies to have them be, independent references of each other.